Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study what are the types of strains and what is Angst Modulus, bulk modulus, and Modulus of Rigidity. So, in types of strain, there are various types of strains under normal load and shear load. Here, under normal load, the load is acting away from the cross section or normal to the cross section, normal to the cross section and away from that, then that load is known as tensile load. Here P is a tensile load which is acting. P is the tensile load acting both the sides. When the tensile load acts on the body, there will be a deformation in the direction of the applied load. The original length of the body here, it is L. After deforming, after applying the load, the deformation is taking place from initial length, that is delta L. So here delta L is the change in length. Originally L, after elongation, it becomes L plus delta L. So the strain, mathematically, it is defined as the ratio of original change in length to original length. That is known as a strain. The physical meaning of strain means the change in length to original length ratio, that is delta L by L. And it is the fractional deformation. That's why the unit for this tensile strain is unitless, no units. Here delta L is millimeter change in length and length is in millimeter. So no units. It is a fraction, delta L by L. So here the change in length, in this case, it is called increment. The length is increasing, that is called increment. And L is the, that is L is the total length of the body. And here the cross section of the body is uniform cross section. When the load is applied, it increased from L to L plus delta L, and L plus delta, and the difference between increased length and the original actual length is the increment in length, that is delta L. This delta L is the change in length or the actual deformation of the material. The fractional deformation or the tensile strain is defined, or in mathematically it is delta L by L. The next type of strain is known as compressive strain. It occurs when during compressive load, when compressive load is applied on the body. In this figure you can see the figure compressive load. The P is acting towards the cross section and it is normal to the cross section. That is the compressive load, compression. During compression also change in length takes place. That is a decrement in length, delta L here. The original length is L, actual length is L, and decrement in L is L minus delta L. So After applying the compressive forces or compressive load, same material would be reduced in length delta L from L to L minus delta L. The fractional deformation again gives the compressive strain, where compressive strain that equal to delta L by L, change in length. Change in length means final length minus maximum length means L minus delta L by L. So L minus L plus delta L by L. This is delta L by L. So in that manner, this is the delta L by L. This delta L by L is known as the fractional deformation. These strains are denoted by epsilon or small e. If it is tensile strain, epsilon T. If it is compressive strain, epsilon C. Epsilon. So this tensile and compressive strains occurred under normal loading conditions. The next type of strain, here it is known as a shear strain. So we can see here, during tensile strain, when the load is applied, tensile force is applied, but the cross section is uniform. And the cross section is uniform. So we can see here the deformation is taking place under tensile load, under compressive load reduction, decrement in length, but the cross section area increases. Under tensile load, length increases, but the cross section is reduced. Whereas under compressive load, length decreases, cross section is increased. So you can see here the cross section is increasing and here it is decreasing, cross section under tensile load. Now, what is the shear strain? Shear strain occurs in a case of shearing load. In the case of shearing load, this is shear strain. You can see this shear strain will be measured by the angle through which the body distorts. This shear strain is denoted by angle that is called phi here. We are considering the body LM and P and one end is fixed. When the shearing load is applied F, shearing load means it is parallel to the cross section. When F is applied on this, then there is a distortion with angle. Because of applying the force F parallel to the cross section, okay, it is applied on parallel. Then there is a distortion moving. The new position is M dash to N dash. It is moved, distorted. The angle of distortion, that is phi. If we consider phi, shear deformation, this means tan phi equal to M dash by Lm. So if we consider this side, that is N dash by Np. N dash by Np is known as tan phi. The tan phi, when angle is very small, then tan phi equal to phi radians. Now, after application of the force, initial, it is the block Lm and P. After application of the force F, then it distorts through an angle phi and occupies a new position L M dash N dash P. The fraction of deformation, the shear strain epsilon S or ES is how to measure it, that is tan phi, that phi equal N dash by P or M dash by ML. So what is shear strain unit? The unit for shear strain is radians phi. So this is shear strain. Shear strain can be observed under shearing load. Tensile strain and compressive strains are observed under normal loads. So you may say that here this F is octo acting normal to the cross section. No, it is on the edge such a way that the parallel position on the cross section, exact parallel position. So it is starting point here, not in the middle of the cross section. Then it is normal. But when it is the cross section here, that here you are applying that is the shearing. This is the cross section parallel. Now another side you may apply. This is also parallel cross section. If you apply here and perpendicular to the plane, that is also parallel cross section. But the true view can be visible in this direction if you apply parallel. So this is, but in principle the concept is that shearing load means parallel to the cross section acts. Shearing load acts or shear force acts parallel to the cross section of the body. Normal load acts normal to the cross section. So we will consider the average, that's it, pass through the centroid of the cross section, so we will make it in the middle. There is the normal cross section. That is the types of strains you have studied. Another types of strain is known as the volumetric strain. The volumetric strain is defined mathematically as change in volume by actual volume or original volume. So by this definition we can understand this volume related to three-dimensional body. This change in volume takes place. It can become apply load or tensile load also. But original volume minus a change in our maximum volume, the difference, change in volume to the actual volume V. So the unit for this volumetric strain is no units. So here very important is that the strains which disappear with the removal of the load are termed as elastic strains. When the load is applied, the strains will develop. When the load is removed, the strains are disappearing, getting disappeared. Those type of strains are known as elastic strains. And the body which regains its original position after removing, on the removal of the force, is called, that is elastic body. Elastic strains, elastic body. That is for elastic body. If we consider the plastic body, there will be permanent deformation after removal of the load. The strains exist even after the removal of the external force. Then the body is said to be plastic. Plastic, when the body is said to be plastic, if the strains exist even after the removal of the external force. So there is always a limiting load, a limiting value of the load up to which the strain totally disappears on the removal of the load. Then that limit is known as elastic limit. So when the stress is directly proportional to strain within the elastic limit, then the ratio is proportionality with some proportional to, then the ratio of the stress and the strain is known as modulus of elasticity. It is defined by the law. That law is known as Hooke's law. So here, the limiting value of the load up to which the strain totally disappears after the removal of the load, that limit is known as the elastic limit. At where within the elastic limit zone, the stress is directly proportional to strain. The stress is denoted by sigma is proportional to strain. Then stress equal to constant of proportionality times epsilon. Then E equal to sigma by epsilon. This E is known as modulus of elasticity. What is the unit for modulus of elasticity? Unit for stress is Newton per meter square and the strain no units. Then the unit for modulus of elasticity is Newton per meter square. So, as I mentioned here, that Hooke's law, his name is the Robert Hooke, discovered experimentally that within the elastic limit, the stress is directly proportional to strain. Or stress varies directly as strain varies. Stress varies. When strain is varying, strain varies in proportional to the stress. Okay, that the stress by strain equal to a constant. That constant of proportionality is known as modulus of elasticity. So, modulus of elasticity is denoted by capital letter E. The unit for modulus of elasticity is Newton per meter square. As I mentioned before, stress is denoted by sigma. Strain is denoted by epsilon. Then stress by strain equal to modulus of elasticity or Angst modulus. Okay, this is what Hooke's law we have studied here. This law is known as Hooke's law. So based on the Hooke's law, we will draw here by using Hooke's law. We will find out the modulus of elasticity we observed here. Now coming to what is Angst modulus. Mathematically, Angst modulus is defined as the ratio between the tensile stress and tensile strain, or compressive stress and compressive strain. E equal to tensile stress by tensile strain, or E equal to compressive stress by compressive strain. This is also known as Angst modulus. The unit for both for compressive strain and compressive stress and compressive strain, modulus of elasticity is both either in tensile or compressive load. The unit remains the same. So, in general, it is denoted by this modulus of elasticity occurs under the category of normal loading conditions. Under shear loads, the shear stress to shear strain ratio, that is known as modulus of rigidity. It is the ratio of shear stress to shear strain. Modulus of rigidity is denoted by letters C, N or G. C or N or G, capital letters G, equal to shear stress is denoted by letter tau, T-A-U, tau, pronunciation, that is epsilon S or ES. Shear stress is denoted by tau. Shear strain is denoted by epsilon S or ES. Shear modulus is known as shear modulus of elasticity under shear load. Here, the shear modulus of elasticity under the shearing load, there is a limit. Within the limit, the shear stress is directly proportional to shear strain. The shear stress by shear strain equal to a constant of proportionality. This constant is known as shear modulus of elasticity or modulus of rigidity. Modulus of elasticity or modulus of rigidity. That is modulus of description of modulus of rigidity. So far we studied modulus of elasticity and modulus of rigidity. The next elastic constant is known as bulk or volume modulus of elasticity or bulk modulus. This bulk modulus is denoted by capital letter K. It is the ratio of normal stress on the face of a three-dimensional body to the strain, that is volumetric strain. This bulk modulus of elasticity comes from the three-dimensional objects, 3D. When the load is applied, what type of load here? Normal load is applied. When the normal load is applied, then there will be a strain in both X, Y and Z directions in volumetrically strain taking place. The ratio of normal stress to the volumetric strain is known as bulk modulus. The unit for bulk modulus, that is Newton per meter square, because there is no unit for volumetric strain. The unit for volumetric strain is 0, unitless. It is a fraction, the fraction of deformation. Whereas the shear strain is having a unit because it is measured in terms of angle. When there is a change in angle of, during change in angle in radians, well, the shear load is applied on the body. That is phi, denoted by phi. Unit for shear strain is radians. Unit for normal strain, again under normal strain, tensile strain and compressive strain is unitless. For shear strains are no units because those are the fraction of deformation in the case of tensile strain, or fraction of increment and fraction of the decrement then in the case of compressive strain. Now it is the bulk modulus or volume modulus of elasticity. First first modulus of, that is the modulus of Angst modulus or modulus of elasticity. Second one is shear modulus of elasticity. And the third one is volume modulus of elasticity. So these are the common fundamentals in mechanics of solids in order to calculate or observe what are the effect of the loads, then what is the output. Here if you draw the ratio of, if you draw the stress and strain curves, we have to draw when the stress is acting on the body, when the load is acting or tensile load is acting, there will be, it leads to a stress. When stress is leading, okay, the strain acts, the strain will be proportionately will occur. The ratio, the slope of this stress and strain curve gives the modulus of elasticity. So we study here the stress strain curve. Here the stress strain curve under tensile load, stress strain curve under normal load. The stress strain curve is focused on only under normal loading conditions. So those are, we are in coming sessions, we'll discuss what is the effect of the shear force and what is the effect of bending moment under various loading conditions, especially shear load. The next thing is that how to calculate the modulus of elasticity concepts and how to apply it, how to apply those principles, or how to apply the formulas while solving the problems. Let us see. Is the problem given here? A square steel rod that is 20 millimeters by 20 millimeter in section is to carry an axial load of, is a square cross section, is to carry an axial load or axial load compressive, that is 100 kilonewtons. Calculate the shortening in length of 50 millimeter. Calculate the shortening in a length of 50 millimeters. L equal to 50 millimeters. Modulus of elasticity, that is 2.14 power 10 power 8 kilonewtons per meter square. That's 2.14 10 power 8 into 10 cube 10 power 3. 1 kilonewton equal to 1000 newtons. 2.14 times into 10 power 11 newton per square meter. Here 100 kilonewtons acting, that means 100 into 10 cube newtons. So convert everything in meters and in newtons. So we know this data, how to find out decrease in deformation. When the load is up, compressive load is applied, we want shortening. Shortening means a decrement in length, delta L. Now here, what is the formula here? We know modulus of elasticity, E equal to stress by strain. Compressive strain here, compressive load, compressive stress. What is sigma C? That is compressive load by area of cross section. We know here 100 kilonewtons and area of cross section 0.0 to 20 millimeter, that is 0.02 millimeters, meters multiplied by 0.02, that is 0.0004 meter square. A, area of cross section. What is the PC? That is 100 kilonewtons, 100,000 newtons. We know the sigma C from the given data. Next, epsilon C. Then epsilon C equal to delta L by L. Before that, epsilon C equal to sigma C by E. From that again, epsilon C equal to delta L by L, that is sigma C by E. Then we want delta L, shortening, a decrement in length, equal to sigma C times L by E. Okay, what is sigma C? That is P C by A. PL by AC into E. This is the formula. If you substitute PC, compressive load 100,000 newtons, L 0.05 meters, AC 0.0004 square meters, and E 2.14 into 10 power 11 Newton per meter square, then we'll get it the shortening length. Shortening. This is the methodology how to solve the problem. Now let us see substitute. Let's step by step procedure. You can see here. Sigma. Why we have started? Why we want sigma? In this slide we explained. Why we need sigma? Because this is the formula. Sigma equal to, if we know the sigma, this is the formula sigma C. Delta L we want output. Sigma C we need, that is P by PC by AC. L we know the length, that is the E. After substitution we'll get it. That sigma C equal to PC by AC, that is 100 in terms of kilonewtons. That's why they substitute here. Everything is in terms of kilonewtons. Now here 100 by 0.0004, that is 250,000 kilonewton per square meter. E equal to stress by strain, then strain equal to stress by modulus of elasticity. Then strain, that is stress 250,000 by modulus of elasticity. It is also in terms of kilonewtons only. All are in terms of, the stress is in kilonewtons, it is in kilonewtons. We have to follow the principle of dimensional homogeneity. If you are following kilonewtons, you follow throughout kilonewtons. If you are following newtons, we convert everything into newtons. Now delta L by L, yeah, final delta L by, this is strain, delta L by L equal to 250,000 by 2.14 in 10 power 8, yes, into L, that is 0.04. This is 0.0584 millimeters. The shortening of the rod is 0.0584 millimeter. It is very small, 0.05 millimeter. So when the load is applied, compressive load is applied. The applied compressive load is 100 kilonewtons. So here, why it is more? Why it is very small? When 100 kilonewtons compressive load is applied, the deformation, decrement in length is small. Why? Because the modulus of elasticity is high. This modulus of elasticity is 2.14 into 10 power 5 megapascal. That's 2, it goes 10 power 5, yeah, 10 power 3 into 3, 6, yeah, megapascals. So the strength of the material, the modulus of elasticity value is very high. That's why the decrement in length is very low. The decrement, the shortening, that is 0.0584 millimeters. Okay, that is the shortening of the rod delta L. They will ask you decrement in length. That is also same as the meaning of shortening of the rod delta L. Next question, if you see, this is the Bloom's taxonomy under Bloom's taxonomy level of applied. Before we have learned the part of understanding of shear tensile strain, compressive strain, volumetric strain, 3 types of elasticity values, that is modulus of elasticity, shear modulus of elasticity, and bulk modulus of elasticities. Now those understanding concepts we are applying, that is called problem solving. We are applying those concepts in the real field problems. Here we have considered some of the problems so that how to apply. Unless we understand thoroughly, application doesn't take place. Now here in this problem, that is a hollow cast iron cylinder is 4 meters long, 300 millimeters outer diameter, and the thickness of the metal is 50 millimeters. He is subjected to a central load on the top when standing straight. The stress produced is It is 75,000 kilonewtons per square meter. The modulus of elasticity of caster is assumed as 1.5 into 10 power 8 kilopascals or kilonewton per square meter. And find the magnitude of the load, the longitudinal strain produced, and the total decrease in length. The total decrease in length. These are the three objectives we have to calculate. The given data is here. The outer diameter is 300 millimeters and the thickness is 50 millimeter. The strength produced, that is 75. The stress produced in it, that is the stress sigma, and the length is L, 4 meters, and modulus of elasticity E equal to 1.5 into 10 power 8 kilonewton per square meter. Now, this pipe is having certain thickness with outer diameter. That means it is a hollow pipe, hollow cross section. For the hollow diameter, what is the inner diameter? Capital D minus 2 times thickness. Suppose it is here. We know the capital D and the thickness is T here, small, and also here. The inner diameter comes, when it comes here, capital D minus, here one thickness, another thickness. That's why it is D minus 2T. D equal to, small d equal to capital D minus 2 times the thickness wall. That's, it is the inner diameter, small d equal to capital D minus 2T. That's capital D here is 0.3 meters minus 2 times thickness, that is 2 times 0.05 meters. Then the small d inner diameter is observed as 0.2 meters. Now if you want a cross-sectional area for hollow cylinder, the cross-sectional area is pi by 4 times outer diameter square minus inner diameter square, that is pi by 4 times capital D square minus small d square. So if we substitute capital D and small d, then we can observe, we can calculate the value of the cross-sectional area of the pipeline. Now what is the first objective? Magnitude of the load. We want the magnitude of the load. How it comes here? Load applied. Stress equal to load by area. From this load equal to sigma times area of cross section. What is the sigma here? 75,000 kilonewtons. Then the value comes in kilonewtons only. Kilonewtons per square meter. Area of cross section is pi by 4 times capital D 0.3 square minus small d 0.2 square. This value is known as the P. Now here, sigma equal to load per area, load by cross section area. What is the P? Load equal to sigma times area, that is 75,000 times pi by 4 capital D square minus small d square. Capital D 0.3, substitute and small d 0.2. Then we can get it. That value is the load. Is the load value is 2.2945.2 kilonewtons. So 2.945 meganewtons. This kilonewton. That is the first objective. The second objective, if we can see, what is the second objective? Longitudinal strain produced. The longitudinal strain, that is epsilon L equal to sigma by stress by modulus of elasticity. The stress by strain, we want here the strain, that is stress by modulus of elasticity. Then substitute over here, then the strain is observed as 0.005. It is the fraction of deformation. That fraction of deformation is unitless. The third objective, total decrease in length, delta L. So decrease in length means the load applied here is the compressive load. Now strain equal to delta L by L. We know the strain value calculated. We want decrease in length, occurs shortening in length, shortening. That epsilon L equal to delta L by L. We know that the value, known value is 0.005. delta L by L, that is the 4 meters. The value of delta L comes here, it is in strain, but if the unit length is in meters, delta L can be observed in meters. Now delta L equal to 4 times 0005, that is 0.002 meters, it is 2 millimeters. So the decrease in length under the load of 2945.2 kilonewtons load, the decrease in length is 2 millimeter. For the material of cast iron having the modulus of elasticity is 1.5 into 10 power 8 kilonewtons per square meter. So the stress developed. So for the stress developed, we calculated the load. The stress is observed here it is 775,000 kilonewton per square meter. Under the stress, the modulus of elasticity, it is the stress to strain, that fraction, it is the ratio of the stress to strain. That modulus of elasticity value is 1.5 into 10 power 8 kilonewton per square meter. At this, under these parameters, and the geometry of the pipeline is 4 meters long, it is 30 centimeters, 300 millimeters diameter, outer dia, and inner dia is 0.2 meters, inner dia, that's 0.3 outer, 0.2 inner, and the length is 1 meter, 4 meters long. So for the 4 meters long, that's why the length of the pipeline is very long. That's why the stress value or deformation value is observed is very low, very small, that is 2 millimeters. 2 millimeters deformation. Now here, if we reduce the length is 1 meter, if original length is 1 meter, the stress equal to strain, change in length, the shortening length, that equal to nothing but a strain value, then it becomes 5 millimeters, okay, 0.5 millimeter, 0.5. Now here it depends, when the strain it is decreases here, if we reduce, okay, if the original length is decreasing, what will happen? The strain will be, if the original length is decreasing, then strain will be improved. If the original length is increasing, the strain will be decreased. But we calculated here the change in deformation or shortening length at a strain of 0.0005, that is 0.05 meters or 0.05 millimeters. At that time, delta L by L at the 4 meters length, the delta is 2 millimeters, that is 0.002 meters. Now, okay, let me summarize what we have studied in this session. We have learned in this session the types of strains, that is tensile strain, compressive strain, volumetric strain, and elasticity, the modulus of elasticity, modulus of rigidity, and bulk modulus, and also very important law that is called Hooke's law, and we applied those formulae in a problem to calculate the stress values and strain values and the applied load values and the total decrease in length, longitudinal strain produced, magnitude of the load, and the shortening length. By using those formulas, the formulas we have studied here, it is only one formula we applied, that is sigma equal to normal stress by normal strain, modulus of elasticity E equal to sigma by epsilon. This formula is derived from the law, that law is known as Hooke's law. This formula is related to, that is modulus of elasticity is related to under normal load and normal strain conditions. The shear load to shear strain, that is modulus of rigidity, and bulk modulus equal to normal load is the ratio of normal load and volumetric strain. So these are very important concepts. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.